Hello everyone. So today we will be discussing about MOSFET amplifiers. So there are basically three types of configuration with respect to the MOSFET. So the MOSFET is represented by like this symbolically. So now the arrow going outside the MOSFET represents that it is an N type of MOSFET. Okay, and if it is going representing towards inside the transistor, inside the MOSFET, it is basically a P type of MOSFET, right? So the corresponding to this, the terminals are drain, source and gate for the NMOS, and for the PMOS this is source, drain and gate. So PMOS can also be represented like with the bubble at the gate terminal, representing that it is an active low device. Okay, this is also a PMOS. So corresponding to these three terminals, we have three types of configuration for the amplifiers, which are the common source, common drain, or which is also called as source follower, and third, common gate. Okay, so these are the three types of transistor what we are going to discuss in this video lecture. Okay, so the first, common source. The source is actually common for both input and output. So this is gate, this is source and this is drain. So common source means the source is common, which is acts as a ground for both input and output. Output is taken across drain terminal. So this is the common source configuration. Okay, and also we represent this in a small signal model pertaining to two-port network, representing that this MOSFET is basically an voltage controlled current source. Okay, that means your output current, the output current which is ID, is controlled by input voltage, which is VGS for this configuration. So in this small signal model, we represent this as common source configuration, the source which is common for V in, and this is drain terminal, source, and this is gate terminal. So the input for the transistor is VGS, which is represented as an open circuit at the input side, representing that the input impedance of the MOSFET is very high. Okay, the input impedance of the MOSFET is very high, such that the gate current IG is almost equal to 0. Theoretically it is equal to 0. Okay, so and the output current, which is given by GM into VGS, this is VGS, the input current, what the output current is controlled by ID. The same we have discussed it in the previous class, previous video lecture pertaining to the ID representing the saturation current equation. Okay, so here coming to the common source amplifier circuit. So here the common source, we bias this is the common source amplifier circuit. So theoretical what we discuss here, which is obtained, the Q point is obtained, or the biasing is obtained using the resistance RD over here, VD, and input signal is basically a VS, which is applied across VGS, and the input signal is applied with the DC source, which is biased, DC biased. Okay, so if we take an KVL at output loop, the loop equation will be VDD or VDD is equal to ID into RD plus VDS. Okay, or basically your output voltage, which is VDS, the output is taken across the drain terminal. So VDS is equal to VDD minus ID into RD. So this is the output equation for the common source amplifier. Okay, and again if we plot the input output characteristics of the same, which is VDS versus VGS, that is input voltage versus output voltage. So initially what happens here, when the input is 0, this is my input, which is VGS basically. When my input is 0, what happens to this equation, or what happens to the transistor here? The transistor will be off. The transistor will be off up till the input voltage is equal to the threshold voltage. Okay, so now corresponding to this, when the input is 0 up till threshold voltage, the transistor is off. Okay, and there is no ID, the drain current is not obtained up till the transistor is on. Okay, so correspondingly when ID is 0 till threshold voltage, your VDS will be equal to VDD. That is what this equation tells about. So when the input is 0, the output is VDD. Up till threshold voltage, it remains VDD. Okay, so now when the input voltage is greater than threshold voltage, now the transistor is on and the transistor will be in saturation region. Immediately it will be in the saturation region because the VDS is very large, and the operating condition or the MOSFET operating region is obtained by this equation, which is VDS should be greater than or equal to VGS minus VTH. Okay, in this case VGS is what we are applying. Up till threshold voltage the transistor is off. Okay, and VDS or output will be equal to VDD, and immediately when the transistor is on for the small value, the VDS will be still large, so that this condition satisfied and the transistor will be operating in the saturation region. Okay, and when the current start increasing, when you keep on increasing the input voltage, the current starts increases and the output voltage starts decreasing. Okay, output voltage starts decreasing here. So this is how the input output characteristics looks like. When the current is maximum, means when the input voltage is very high up till VDD, then what happens? Your current will become 0. Sorry, the output voltage will become 0 in this case. Okay, so this is the input output characteristics, and here for the transistor to make it work like an amplifier, you operate in the linear region of the amplifier circuit. This is the linear region, operating region of the amplifier circuit. So for this, if you consider this as the operating linear region or the operating region for the transistor or the circuit to work like an amplifier, so then what happens? You apply the VDC or the VGS. This is your VGS, and you operate in this region, which is basically an operating region, and this is your output voltage, and this corresponding to this is your VDS. Okay, and corresponding to this is your VGS. So now here when you give the input signal from 0 to high, what happens? Corresponding to this projection on the curve, the output goes from 0 or the reference to low. When the input is going from 0 to high, the output is going from reference to low, and when the input is going from reference VGS to low, what happens? The output is going from reference to high. So basically in this case the output is inverted with respect to input. Okay, because of this negative slope, the output will be inverted with respect to input. Okay, so this is the operation of the common source amplifier. So theoretical common source amplifier. So practical, what happens, we are going to bias this circuit. So the practical common source amplifier will be consisting of the biasing circuit, which we bias it using the voltage divider bias R1 and R2, and this is source resistance and this is drain resistance. Okay, and this is VDD, right? So this will be the practical circuit for biasing purpose. So now for to apply the AC signal, biasing purpose means, so to get this operating point VGS and VDS, this Q point, okay, to get this Q point we are going to bias this using the voltage divider circuit, what we are representing here using R1 and R2. RT acts as a load line and RS is the source resistance, and for the common source we are taking the output across drain terminal. This is the biasing circuit. Now for the AC circuit, what happens, we give the input signal, AC signal, using a signal generator or the signal source, and we have the capacitor, which are input capacitor, coupling capacitor or output capacitor, and bypass capacitor or CS, which is connected across the resistance RS. Okay, so now when for the small signal analysis of the same, we are going to represent this using a two-port network using a small signal model. So before we do that, there are certain things that we have to do, or that we have to follow. First is, all the DC supply should be shorted. That means all the DC supply should be connected to ground. And second, all the capacitor should be shorted. Shorted means, that means all the capacitor acts as a short circuit. So now, and along with this, any resistor associate with bypass capacitor will be neglected, because this is the bypass capacitance, which is CS. When this is shorted, the current will flow through this low resistance path. Okay, the current will not flow through the resistance RS. It will follow the low resistance path. Hence we are going to neglect this resistance bypass, the resistance associated with the bypass capacitance RS. Okay, so now the modified circuit will be R1, R2, this is neglected, RS is neglected, and this is RD. All the capacitors are shorted and DC supply is connected to ground, and this is your V out and this is your Vn. Okay, so this is the modified circuit. Now to represent the same using small signal model, first we draw the third step here is draw small signal model for transistor. Okay, so now here for the transistor, common source, the source is connected to ground here, the output dependent current ID, which is equal to GM into VGS. This is our VGS. Okay, so in this case we are neglecting the channel length modulation. Neglecting the channel length modulation means R0 is neglected. Okay, R0 is neglected. If we are not neglecting the channel length modulation, then R0 will be considered and R0 will be present here across the dependent current source. Fine. So this is the small signal model for the transistor. Now adding the other network components, that is R1. R1 is connected from gate to ground here. So this becomes R1 and R2 are parallel. So this is V in, and here RD is connected from drain to ground. So this is RD, which is connected from drain to ground. Okay. So now here, to do the AC analysis, that means to find the input impedance, output impedance and gain. So first, input impedance. Input impedance is Zin, what we see with respect to input terminal, that means input voltage and input current. Okay, Zin is nothing but with respect to input voltage and input current. So when we see with respect to this two terminal, that means V in and I in, the R1 and R2 are parallel. Okay, so here R1 will be parallel to R2. So this is the input impedance. So similarly, to find the output impedance Z0, so Z0 is formed when we see with respect to the output terminal V0, which is across RD. Okay, and corresponding to V0, this is the I0, the direction of the current flow. Okay, so this is my I0. Okay, and here this is my ID, which is flowing from drain to source terminal. Fine. So now corresponding to this, my Z0, when we are finding the impedance, all the other voltage source and the voltage source should be shorted and the current source should be open. So here when we short this input terminal, input voltage source, the R1 and R2 will become short, and here VGS is anyhow open circuit. When V in is 0, VGS will also be 0. When VGS is 0, this current becomes, this current source, dependent current source becomes open circuit. Then you left with only what? R0 and RD. Okay, so this will be my Z0 corresponding to my V0 and I0. Okay, so Z0 is V0 by I0, which is equal to RD parallel with R0. Okay, since R0 is very large practically for the MOS transistor, so the Z0 can be approximated to RD. So this is output impedance and this is input impedance. Okay, so now to find the gain, so the output voltage V0, so since R0 is 0, so the R0 is infinite, the current will flow through the RD itself, which is in the anti-clockwise direction. That means, so ID is equal to minus I0. With respect to I0, it is flowing in the opposite direction. So my output voltage is I0 into RD. This is my output voltage, output impedance, which is approximately equal to RD. So here I0 is nothing but minus ID. Okay, minus ID into RD. ID, which is nothing but GM into VGS, GM into VGS into RD. So here VGS is nothing but your input voltage itself. So my VGS is GM into V in into RD is nothing but my V0. So finally, taking this to the denominator, V0 by V in, which is nothing but gain, is minus GM into RD. So this is the expression of gain, minus GM into RD. Right? So these are the AC parameter or the performance parameter of an amplifier circuit, particularly for the common source amplifier. Okay, so in the next video lecture we will discuss about common gate.